Yeah, okay, perfect. So, hello everyone. So let's get started. Today's speaker is Dr. Lingling from MIT. She's now a postdoctoral associate at MIT with a joint appointment between computer science and artificial intelligence laboratory and the research laboratory of electronics, advised by Dirk Englund and Mania Gubadi. She received a PhD degree in electrical engineering at Stanford University, advised by Shanui Fan in 2023. Prior to Stanford, she did her undergraduate research at Yale University, Applied Physics, advised by my friend Owen Miller. She was a research intern also at Google in 2022, working on chip designs. She has been very productive, publishing over 30 papers in peer-reviewed journals and conference venues, giving several invited talks at Columbia, Boston, Nokia Bell Labs, Google Research. She also has 2 US patents, and she's the recipient of several awards, including an engineering fellowship from Stanford, Clio Presenter Award, ECE Rising Star Award, and a few others. Their research interests lie primarily in theoretical and experimental studies of nanoscale and quantum photonic engineering for heat transfer, optical force, sustainable energy, photonic hardware, and quantum computing. And Lingling is really a rising star in this field. So, Lingling, it's a pleasure to have you here, and the floor is yours.
Thank you. Good afternoon, everyone. I would like to start by thanking my host, Francesco, for the warm introduction, and thank Model and the EDS committee for their invitation and their excellent organization of the talk. And my heartfelt thank you also go to all of you and people in the Zoom for joining us. And today, I'm going to talk about the deep co-learning along the frequency dimension to build this energy efficient system. So in this current age, we are living in a region of the deep learning. But before I dive into the specifics, I would like to briefly introduce and outline my research journey. And during my time at Yale and also at the initial phase at Stanford, the initial research focus was on the fundamental limits for those optical response. And I have studied a series of comprehensive theories to build and describe the fundamental optical interactions, including near-field heat transfer. And during that time, I was have very close interactions with Francesco, who are expert to build the, for example, there is one particular interaction that is our focus of the fundamental limits, mostly for single frequency limits. But Francesco and his collaborators worked on very groundbreaking works. And for example, they introduced, if you have the time modulation, very recent work, and then you can combine multiple frequencies, and this is very promising to break those optical interaction limits. And another example of this inspiration has come from my investigation of optical force and the near-field heat transfer. And again, in this area, Francesco is an expert, and I constantly get inspired by his work, optical force or optical torque in the non-reciprocal area, and also you have some near-field heat transfer works. So gradually during my PhD, because PhD is such a long years, and my research interests gradually shifted from those fundamental research to more applied-driven research. And for example, I started, but most of this research, although the topics may have evolved, but the underlying principles actually share the same physical root. For instance, in this talk, I'm going to talk about this photonic computation using the components from those optics. And in this case, we talk about this, we use a frequency dimension, but actually the underlying physics rely on, for example, the time modulation, or you can even connect to non-reciprocity. And another example is that because we have those computation hardware, and the motivation for us to develop the computation hardware is because we are facing the energy crisis, but the energy consumption has largely focus on, for example, other areas such as your building or your daily life. So those energy consumption also takes a big concern for us. And in particular, if you integrate those computation hardware into the data centers, it will contribute or accelerate those global warming. So with these considerations, I continue to study this thermal engineering, and this also is important to focus on some particular very important approach, such as relative cooling. And it may seem that not relevant, but relative cooling is just a far-field counterpart for this near-field heat transfer. So, and most of these thermal engineering projects actually necessitates the study of those tools are developed in those fundamental research, such as to do the inverse design for the photonics. And we also are interested about how much energy we can extract from this relative cooling. So there will be other fundamental limits related in this area as well. So my research actually formed a closed loop, and today I'll be delve deeper into a latest work that is about the same data for the deep co-learning along the frequency dimension. So to build the energy efficient system. Deep learning has been the cornerstone for our artificial intelligence age, and it has brought a number of applications ranging across a diverse range of tasks, from those image recognition, language analysis, all the way to the robotics. But in particular, we can divide or roughly divide into two major categories of tasks. For example, we have inference and the training. So for example, the training process actually represents the essential part of the learning, and envision a robot that is trained or designed to assist the individuals that have faced the difficulties in feeding themselves. And we would like to show the traditional training method where the robots are trained based on fixed data set. It will be hard for them to, for example, as this video would indicate, that the robot cannot find the particular location for the mouse, and then it will be very easily for them to struggle to perform this feeding task. As a consequence, it's actually caused a lot of dangerous or even hazardous scenarios from this insufficient real-time training. In contrast, if the robot can adapt to the real environment or the real time, so whenever it encounters a new person, it will be able to reconfigure the model or retrain itself, so that in the second model, I would like to show that this robot can train themselves on device, and then it can find the location of the food and adjust its direction of the action, and also locate the precise position of the mouse, and eventually it can feed the person precisely. So the first kind of traditional training is insufficient, and the second kind of training based on on-device training or real-time adaptation will change the situation. So actually, this type of training has a particular name called on-device training. And remarkably, most of our people from photonics area will be able to develop this kind of technology. Imagine there will be a user that can send those data to the edge devices. For example, it wants to train the model that can particularly fit, for example, his or her kids. And then this data, for example, would be their children's photos. And for the edge devices, here it sounds a little bit strange for us. It represents those devices that has limited memory or battery, for example, your phone or your camera. And in this case, suppose we want to train a model, and this is data that is from, if you want to train the model for the edge device, and this is a standard DRAM memory. And then most of the inference tasks can be performed with a very small amount of memory. But if you want to do the training job, it actually much more exceeds this on-device memory. So that represents, this is a challenge. But the particular procedure we would like to perform is to send this data, send those models to the on device. So it's not to send it to otherwhere to avoid those privacy challenges. For example, I would like to show you that if you train the model and put this model and data on the device, so you can much more preserving your data safety. And in particular, we can introduce that the photonic training can bring a lot of benefits. For example, we can have the low latency, low energy consumption, as well as the high bandwidth. To demonstrate the capacity of the photonic computation, we will need to show that the current development for the machine learning relies on the neural networks. So in order to map this neural network to the photonic devices, we can find the one-to-one correspondence based on those spatial meshes. For example, you have this waveguide, and then you can launch this X0 into the waveguide, and then each of the layer, for example, on the upper side, it represents what we call as the this algorithm as a parameter, and in the lower part, which is like the locally defined this permittivity, it will be the hardware parameter. And most of the cases, we will need to do, this is a linear layer, and this is a nonlinear activation layer. Eventually, we get the first layer output, and by connecting multiple layers together, we can build neural networks. This is essentially the deep learning. But there is some challenge with the current neural network training. For example, if you separate this theta algorithm with theta hardware, there will be a gap, and we call this as a simulation reality gap. So for example, you cannot precisely model this system with your digital model. And secondly, you will be facing the situation where you do many measurements in order to fit in some parameters. And this kind of fitting is actually very inefficient. And thirdly, we will be needing some additional computation, because once you get this model, you actually train this on your local computer and then map this on the physical experiments. So this process actually adding those additional computation overhead. So from here, we would like to introduce a new scheme that is to do the deep co-learning that the device and the programming can co-evolve. And there are two parameters that we introduced before. And essentially, we want to change these two parameters at the same time. And we can map this function into the given hardware. Eventually, this co-evolving process can form the closed loop. And you can train this hardware and software at the same time. So I think last time, as Francesco just mentioned, Biodelli also takes the same philosophy for the digital hardware. So this will be the best strategy to develop the hardware accelerator for the deep learning age. In this case, what we recently have is in situ light propagation using the spatial meshes. So the spatial mesh means you will need to have this waveguide we introduced before, and this is the algorithm and experiments both have been demonstrated. But in this case, we can dive a little bit deeper into the detail. For example, you have this X0 put into W1, and then you have this Z1 as an intermediate output, and automatically you get this loss as this XL as the output, and you can also get this loss. And in a backward propagation, you should in a backward propagation, you can get this light to do the interference with the original sending incident light, and this interference term will correspond to what we eventually care about, which is you firstly have this loss, and then you do the gradient with respect to those physical parameters. The caveat is the system is static, so that means you have the thermal modulation. You change the local temperature to change this phase. So this is essentially is a reciprocal system. There is no modulation in this system, and the backpropagation can be done very simply by putting the same hardware and then just put the output port as the input port for the backward case. So from here, we can see why we would need to think about why we since the spatial mesh, we have done both the inference and training, it seems like we can stay with that and don't do anything else. But it's actually not sufficient. For example, in the spatial mesh, if you want to do this 4x4 matrix multiplication, you will have hundreds of phase shifters. And in another example, in this quantum computing, you need to have hundreds of mirrors in order to get this 100 outputs or inputs. So another example is this LiDAR device. It actually involves hundreds of antennas, even to just so it seems like still small. For example, if you use hundreds of antennas in the nano-fabricated chip, it takes 100 millimeters squared, but chip area is very expensive. So you essentially would like to reduce the area. And all those indicates that suppose one day we want to realize the functionality from the phone onto our photonic hardware. So what would be the area that we would essentially take place? So it probably would be the entire room, like the ENIAC edge. The reason is that photonic hardware or most of the photonic components, because it's not very easy to scale and it usually takes a larger space. So imagine that currently we have the 22 nanometer process in the standard foundry, but the photonic devices usually takes the micro as the minimum process. So that would be a very huge difference. So with that, we would like to think about what stops this scalability. So whenever we want to use light to do certain performance, we utilize the degree of freedom in photons, such as we have used this amplitude phase position. This is standard, and then we can also use this orbital angular momentum or spin angular momentum or propagation directional time. So this would indicate, for example, if you have n inputs, you will need to have n ports. And this applies to almost every hardware that is using the photonic spatial degree of freedom. But in this case, as our title suggests, we will need to use a new degree of freedom, which is photon frequency. For example, if you can map this degree of freedom into the different colors of the photon, and in this case, you can change this multiple ports into just one port. And this would definitely make the device much more compact. So again, we would adopt this approach in a spatial spectral engineering, and to make the system much more compact to do the computation. And to illustrate this principle, we will use the convolution to show the spectral capacity. So I believe most people have done the signal processing or image processing. And during this process, if you want to extract useful information or features, it is essential for us to do this convolution. As an example, we show that suppose you have this encoding of data along the frequency, and the A is the input, and this S is the kernel. And the output from this input to the kernel would give us the B, which is the output. And in this case, we use the simple kernel as an example, and then the mathematical relationship can correspond X to A to B very precisely. So particularly, we want to draw attention to this small s, which we would utilize to represent the convolution kernel later. And with this as an example, we would like to perform the convolution based on this hardware. So that means if you have, for example, the standard device we can do is to do the temporal modulation with a ring resonator. In this case, the input is put into as a frequency comb, and then the waveguide can hold this frequency comb and launch couple into this ring resonator, which we have this temporal modulation here to perform the to apply the voltage into this ring resonator. And from here, we can put also, for example, this input would be corresponding to a temporal signal, and the frequency domain, if you do the convolution, is just temporal domain. You do the multiplication, which is easier to understand and also easier to perform in the physics. So in this case, this input would be multiplied by this, for example, if you have a transformation in the time domain, you just do this multiplication, and then the output should directly give us this convolution result. But what's particularly interesting is that we need to program this SOT in the modulation. For example, we use this deep co-learning language is that if you have this SOT, which is represented by because it's at the theta algorithm, and you know what kind of transformation you want to have, and this is a temporal modulation you can control. And then we need to find the relationship between this hardware and algorithm. And in this case, is a simple relation, but the particular notice is that it is a deterministic process, so that this analytical relationship can give us both these for example, you have the phase modulation and the like the amplitude modulation. So these two modulations can be determined for example, you can determine this analytically. So this would not involve any kind of additional computation. So this is a benefit for us to do the convolution with direct modulation that can be configured analytically. So the experiments we do, so far we talked about the theory, and then theoretically we found the relationship between the hardware and control. And now we would like to demonstrate what is the experiment? Can we verify this? And the answer is yes. And this is a schematic for us to operate and launch this input waveguide. So suppose you have a continuous wave as a laser input. You have the modulation to do the electro-optical modulation, which we call as EOM here. And after you have the modulation, you will be able to form a frequency count here. And this is a coupler and launch into the ring resonator and get this output. And this is an experimental photo that we have that have a one-to-one correspondence. The highlight is that we are currently using the fiber system, and this is because it's a bulk components. And the reason is that we do have the access to the standard chip development, but the benefit for us to use the fiber system is that because the free spectral range, which is a unit for us to have the frequency spacing, is relatively small if you use a larger ring. So the fiber system is a larger ring, and fiber also essentially has a lower loss compared with the chip ring. So in this case, the overall quality is actually higher than the chip system. It's better to demonstrate this optical computation with this setup. So in order to demonstrate the convolution, we show this schematic that, for example, if you want to prepare a kernel that can do the edge detection, and so this case, we have a slightly larger like the central element, because we want to highlight the original signal as well due to our like the experimental quality. And in this case, we start from this kernel. This kernel will do the two jobs. One is first, it can highlight its original signal. It can also extract the edge signal. So it can do the, for example, the image recognition task. So in this case, we have this input that is represented by the frequency count. And after this convolution, you should get another frequency count that be mapping to this convolution result. So here we have to get the confusion right. So here the x-axis represents the frequency, and each frequency we start from this central baseline frequency, and then it's separated by this omega r, which is like capital omega or omega r. We use this interchangeably to represent the free spectral range. So this is the unit of frequency in our ring system. And with this, we can show the series of experimental results. So the frequency count we input into the system is by this modulation. You can see it here. And we have both the real part and imaginary part depending on how you change the global phase. And the output here, the highlight is that we didn't do the fitting of the experimental result, but rather after we have prepared the ring for the kernel and then directly launch the input, and we measure this output. This is the direct output, which we labeled as this orange bar. And what we expect from what we draw as this cartoon figure is shown on the green bars, so that these two can show compare with each other. So both the real part and imaginary part can agree very precisely. Or we can even improve this quality. And in our paper, if you are interested, you can find a lot of examples to show the capacity of this system. So essentially, we can build arbitrary kernel or arbitrary convolution operation. And if the system, for example, if we can improve the quality of the system, we can even do even better number of the frequencies. So this is like, for example, the proof of concept. And but for example, this real and imaginary part to introduce the notation here. So this is the capacity for us to think about the 1D convolution. So the 1D convolution is for example, the very basic and very standard operation, but we are not satisfied by that because most of the data in our data, except for those audio signal, actually most of the signal would be the 2D or even 3D data. In this case, we can put the 2D signal, 2D convolution converted to the 1D convolution. So I would like to show you the standard process. So I developed this algorithm to convert all the high dimensions to the lower dimensions so that our previous system can still work. So this is the input that we can flatten this matrix into the 1D vector. And this is, for example, we put as a ring the transformation matrix. And we put these labels here just for convenience to know what kind of kernel, like SON here. So we put this central element because we care about the symmetry here. So we put the central element in this diagonal direction. And second step, like the second way to consider that is that we put additional neighboring elements onto the neighboring sides. And similarly, we can map the entire matrix with this 2D, like the kernel matrix. So this kind of a little bit complicated, but there is a mathematical relationship I will introduce in a later to show what is a one-to-one correspondence. And I also demonstrated that it is true that for the 2D convolution, if you just do this matrix multiplication with this vector, you can get the very precise, like the output can get you the 2D for example, 2D convolution result. So this is very exciting because suppose you don't need to, for example, so some people, if you care about the computer vision, you will know that the higher dimension like the benchmark is usually much lower than the lower dimension data processing because processing those higher dimension usually represents a challenge. But now, actually, we put everything in the equal foot. So every dimension operation is just a 1D convolution. So that will be a remarkable change in the photonic domain. So in this case, we would consider like this mathematically how we can convert this 2D or even 3D kernel into a 1D kernel. Now I would introduce this mathematical relation. So this S is the small lowercase s is a kernel, and then the F is a matrix, or this is a cube. And we can, for example, in order to label this F as a kernel, we have both the P and Q as the X and Y direction, and the T is to label this Z direction. Suppose this is into the paper. And in this case, we also need to consider, as you can notice in our last slide, we have those zeros to hold in between different rows. The reason is that we need to consider the input size. For example, we need to match those input size into the matrix to do the multiplication. So you can see this L2 is the input data size. And this is to introduce, we label this as, for example, from the minus P1 to positive P1 to put every element as a central element wise. So and L2 and L3 correspond to the input size. And to perform this particular task, there is one kind of task that is very interesting, which is the human action recognition. So most of the cases, we would need to, for example, you put the video and you don't know what is the person doing. And in this case, we can perform this, for example, in the temporal domain, we can do this Laplacian operation. If you discretize in the, suppose this is the t-axis, and then you can do the Laplacian operation here. And this x and y axis, you can do this Laplacian recognition to do the action. For example, you have the eye detection in the XY plane, and the Z plane, you do this differentiation to know what kind of action is taking. So we have this kernel, and we will demonstrate how to do this with our convolution ring in the next part. So in this case, we would like to import the video frame. So we would like to clip this video into a sequence of images. So we have the person in the video actually waving the arm upward. So as time evolves, you can see that the arm part is raised upward, whereas other parts of the person is putting a static. So this is useful because sometimes you would see the very accurate and every part of the person will be moving, and that's not an effective example to show the action recognition, because we know the standard, for example, eye detection, this is the output from our result. So in the middle, we show that the person, only the arm part is highlighted, whereas other parts are staying at the background. So what does it indicate? So the standard eye detection in the first and the last slide only is, for example, the 2D signature for the convolution. But if you can highlight only the moving part, but silencing those X and Y direction, because it's not relevant to the action moment, and that is the most effective way to demonstrate this system is actually doing the 3D convolution. So we can even do higher dimensions. The limit is that most of the for example, the input components would require us to do for example, many frequency size. We don't have so many frequency size. And this part, although this is a very exciting result, but this is also like just the simulation result. But we have the experiment going on to demonstrate this. And the limit for this, because you can see this is a 50 by 50 by 5, like thousands of components will be involved in order to control this modulation. Even though if you have the, for example, 1 megahertz, the smallest free spectral range, you still need to have a large modulation strength, which is not capable in our current experimental situation. But we have in a good progress of that, and I hope in the next few days, next few time you see this, like to demonstrate in experiments. Yes.
So ultimately, the number of frequency sites you can use is limited by
the group velocity dispersion.
Yeah, exactly. So realistically, what do you think would be like a practical limit, not really fundamental?
Yeah, the group velocity dispersion is not a limit on the chip, because for example, in the lithium bit range, they actually operate. You can choose the operating range, and then most of the telecom range, this actually has no almost negligible group velocity dispersion. Also, in our fiber system, we have done a detailed calculation to show that we can support 1,000 frequency size that can be seen as an equal spacing to each other. So in this case, the group velocity dispersion within 1,000 frequency size are indeed negligible. But the another strength is that, for example, the current modulator, like the EO modulator we use, like for example, it can at most get there are some high quality ones, but we use some not very standard ones. So it can only support a number of modulations. So
the size of the ring, I guess.
Yeah. The larger the size of ring, the better the modulation would be, because the larger the ring, and then the smaller the FSR, and then the more modulation size we can control. So if you go to a chip, for example, the lowest FSR is like tens of gigahertz, and then I suppose the current AWG arbitrary waveform generator, it can at most get hundreds of 100 gigahertz. That's the most. So in order to overcome that limit, we are currently also working with for example, there are some RF designers at MIT. So they can design the CMOS chip that can satisfy the need for the control unit. So it actually, without those commercial AWG, you can get a better performance. Yeah. Yes.
Actually, I have a question about the flattening.
Yeah.
So, if you do any computation with like digital computer, like laptop, whatever, those flattening algorithms already exist. So
Yeah, they call this as a general matrix multiplication that exists, but it doesn't affect the computation cost. So for example, it is shown that when you do this matrix with the general matrix multiplication, it's actually, for example, my flattening is to flatten the kernel, and their flattening is to flatten the input. So I have explicitly checked this out. Also, I also flatten the input, but you can find the correspondence that their GMM will make the kernel, for example, every time they will make the kernel as one dimension, and then the input as for example, this candle matrix way. So every time you cannot reconfigure, you need to do this one-dimensional kernel, and then the input will be the 3 in the 2D. So that doesn't apply for our case, because in most of the transformation, we can put this as a matrix way, and the input is a 1D. So physically, there will be a different implementation to do this. And mathematically, I think both can work eventually. Both are correct, but this would work for our photonic system. And photonic system have the intrinsic benefit. For example, you have the low energy and high bandwidth, and this would not exist in the digital system.
Actually, my question is not about whether this is the correct way for that. I believe this is the correct way to do for. I just want to mention that in the hardware, everything is stored in a 1D sort of representation, because the only dimension is the distance between two digits in the hardware. So everything to the bottom is stored in 1D. So there are a lot of work has been done to find a more efficient algorithm to do every operation that is optimizing over the way that you store those digits. So I think those are essentially very similar questions, like how do you represent digits in hardware or in a photonic hardware? Like what is the most efficient?
Like for example, you can do the quantization, or like for doing the pruning of the neural network, or related, for example, neural architecture search, right? There is some.
I mean, even more about, like, suppose you're working with matrix multiplication, and you do it in a recursive way. You need to get the matrix sub-blocks. And then you want to store those sub-blocks in a very organized.
This was related with memory, right?
Yeah, exactly.
So I have the next couple of slides to talk about. So this is exactly what I'm going to talk about. So the main limit, I think the limit for both photonics and the hardware is the same. Is a data movement bottleneck. So that means you have the computing, and you also need to process the memory. So the memory, usually we have the 1 gigahertz storage, and the computing, because as I said, you have hundreds of gigahertz, but the limit actually put in the memory side. So there is a data path that you need to pre-compute those data movements from those memory to photonics. So the reason, the method I developed recently after I came to MIT, because I have a joint employment with CS department. So we developed this control plane reconfiguration. So that means you can do the, as I can show you later, is the standard way we do photonic experiments is actually very crunchy, right? You set up this AWG, and then you measure this and set up, and it's actually by hand. But how does our computer work? It actually have a clock, and then you have those we call this, it's a little jargon, but it's called as RTL. So you have the control signal to show. So at this clock you do this, at this clock. So everything you set it up and then it's done automatically. So from here, this is a control plan to do the. For example, there is a standard way. My current demonstration is for example, photonic computing operating at 4 gigahertz. And then this would mean that if you have 4 inputs in digital, and you do the count action. So there is a standard network. Like for example, do you know the congestion control? Like for example, when you do the video, the speed of that internet is slow, and then you can reconfigure real time how to play the YouTube video. And this will require us, for example, if you are running this hardware and you don't know what kind of control unit you would do, and this would require us, for example, in a network language, you have the package, and then you figure out the hardware, and then you accelerate the process. So I have built this, for example, RPG hardware. It's a little bit there are many components, but the highlight is that you can use the Linux RPG configuration, and then you put your RTL in, like for example, you write this word log, and then put it into the Linux, and you have the like an EDC convert to the amplifier, and then this is another amplifier, and also you connect to the optics part. So this part, optics, actually is exactly the same as what I've done before. So this, you have the modulation and you apply in the fiber. This is the later. So I separate these two figures apart, but you should imagine that these are previously connected. So from here, you can get this as an input. So these two figures can be connected, and for display purposes, it's a little bit separated. So to connect this, and eventually the effect we can realize, and this is the work that I recently presented at the ECMC conference, which is a network conference, because I have an advisor in this part. And we built this, this is also some part of the Verilog have already been built. And then what we built is that, for example, this 100 gigabit per second Ethernet, you can launch those real-time packets. And then in this case, we have the DAC and ADC. DAC and ADC can exist as our previous figure shows. So this is a so previously the schematic, now it's a real figure, real setup. So the work is that, for example, you launch this command, you set it up from the FPGA board, and every computation can extract, can operate. For example, after the digital, you go to the optical, and you also have those multiple inputs of the frequencies. So eventually, you will be able to get this output to, for example, you do the image recognition, and you can figure out what kind of digit it represents. Oh, sorry. Yeah. So this is the FPGA work, and to connect to our deep co-learning language is that we have this algorithm, and we also know the hardware. But the first setup is that we don't know what is the analytical connection between these two. And in this case, we developed this as my PC group has previously called as a synthetic frequency dimension. Like we have used this synthetic frequency dimension to connect the input to the output by this transformation, and then you have this modulation here. And the second part is the in situ training, which is what I demonstrated before. So you can do both using the FPGA setup. You can do both for example, the forward inference and the backward for the training. And in this case, we utilize multiple frequencies, so it's still in the frequency dimension. But the particular part is that because it is a very high efficient hybrid digital and optical part, you can do this very efficiently. So there are challenges with computation, and previous work has a low scalability and low energy performance. And now we can improve this by, for example, in the scalability part, we have higher dimension computation realized in just one ring. And we also have those scalability with the input size. And for the sustainability part, we have realized without any optimization. For example, we don't introduce additional computation overhead, but rather we do everything on device. And secondly, we can also improve this energy efficiency for those hundreds of gigahertz operations per joule. That is, we calculate this, and it's roughly 400 orders of magnitude higher than the CPU or GPU. And from here, the reason for us to build this hardware is to reduce the energy consumption. But as I mentioned before, most of the computation will exacerbate those global warming, and the thermal engineering actually play a central part. So that means if you live a world and then you solve one problem, but there is a bigger problem waiting you to solve, and that is, for example, how to do the sustainable energy approach. And the frequency is still a very important component. I would like to say, for example, if you have for most of the reciprocal objects, the emissivity would be equal to absorptivity for every frequency. And then in black body, it has unity emissivity, and that means the absorption of the energy it emitted will always be unity. And what we do is to do for example, this now is not algorithm, but it's for example, how to do the functionality. And this hardware is this emissivity profile. And we would engineer this material based on, for example, photonic design or some of the material science languages. So this is two works that I would introduce. One is to generate light, and one is to reduce the temperature in the buildings. And the first part is to, for example, the lighting will peak during the nighttime, and we would like to build the energy source that can work during the nighttime. And for example, if you have learned about the thermal engine, and this is a standard language, for example, in the daytime, you need to put in the solar cell, and then it will attract those light. And in this case, the hot side, in a heat engine, we already have the hot engine and the hot side and cold side. But in the nighttime, you need to have this different results. So you put this earth as a heat source and the outer space as a cold sink, and then you can extract new energy. So this is a standard operation as a radial cooling, or both for the daytime. This can work for both daytime and nighttime. And the reason for radial cooling to work is that you have the wavelength range, and there are separate regions. And what stops us to utilize the outer space is because there is the atmosphere. So we use sunlight almost in every place is our daily life, but we have never go to the sun. But in order to use the outer space, we also don't need to go to the universe itself. So we need to utilize this transmission window, especially, for example, the largest transmission window happens in the 8 to 13 micron. And if the black body emissivity, it will have the unity emissivity for all the frequencies. But if you can build the photonic device, for example, this can operate in the daytime, so it can reduce the temperature by 5 degrees during the direct sunlight, even at Stanford. But the reason is that it can work because it has a very high emissivity during the long infrared, essentially. So it can reflect the sunlight, or you also emit the sunlight, emits its own energy, so it can reduce its own temperature. So we have the theoretical design for this photonic device, and this is eventually what we get as a photonic device by putting different layers together. So there is some difference, but nevertheless, this can work. So we have shown the capacity. For example, this is a previous experiment to extract the energy, and this is our work too. For example, it operates if you put it on the roof, you can extend the heat to the outer space and generate light. And another example I showed to the radial cooling part is to show you to the HVAC. For example, what does HVAC mean? For example, we are currently going to get winter time. So winter time, you need to turn on the heater. And this would mean the, like, for example, the outside is colder, and then we want to reflect, if your wall can reflect your energy inside, and then you don't need to turn on the HVAC or air conditioning, and then your energy gets saved. So the operations principle is that in the summertime, you need to reflect the energy outside, and in the winter time, you need to reflect the energy inside. So for the year-round operation, especially for example on the East Coast, it has summer and winter, and you will need to have those energy saving the walls to be very thick. That's the principle. But this kind of thick will actually have a lot of, for example, not so ideal because it will be very bulky, and it's also not so beautiful. Because sometimes you want to have different colors. And we developed this kind of thin film, which can put on the wall as a wallpaper. And the reason for us to work this out is that this is the solar emission spectrum, and this is the thermal radiation spectrum. The reason for us to care about the color is because in the visible range, your eye will have different color sensitivity, whereas in the infrared range, we will need to have the thermal property. So this is by material engineering. We have those two-layered material, and this is a thermal like the SEM image correspondence 1-to-1. So the upper layer is to do the mechanical stability, and this IR transparent pigment particle is to, for example, IR range represents thermal range, and the pigment will do this color for you, and this like the bottom side is the aluminum, which is to reflect the IR range, so do the thermal reflection. So we separate these functionalities, and particularly this pigment would correspond to get those different colors from this system. And to show the capacity, we have the different colors that correspond to the visible range, and this is a small, medium, and long wavelength range to get our eye sensitivity to do the combination, so that eventually you see this color, but you have many degenerate combinations. So we have these different colors to show in the visible range, and at the same time, you also have those low emissivity. Low emissivity seems like very jargon word, but it actually refers to the high reflectance. For example, most of your white clothes would be the low emissivity. And what we built here is that not limited by the color, but rather you have different colors. Like for example, the white certainly has a high reflectivity in almost all the frequencies, but there are some peaks. These are details, like because different atoms would have some absorption curve. So this would correspond to the mid-infrared range, and we can fabricate this very easily. And this can be like you can destroy that as well, and it can also be very easy to endure those environments when you have the different temperature or different acidity. And this is the evaluation for different places. And eventually we build this all year round evaluation for the entire United States. And the highlight is that if you apply this building walls to the building walls, you can save like 10% of energy for the entire energy use, and you can reduce about 3% of the carbon dioxide emission. So this would be very good for our environment. So we have talked about this thermal engine, but it can still be put into the deep co-learning language. For example, you have certain like the physical system, like you build this layered photonic device, and you also want to have some functionality, like you want to generate light passively without any charging. So we forgot to mention that the previous light generation actually don't need to have any electricity plug in. So this would be very useful if you don't want to have any electricity bills. You can actually rely on this for the entire life. The second way is that we want to read the algorithm parameter would be, we want to preserve energy. We want to reduce the air conditioning use, also reduce the electricity bills. I think electricity is very expensive many places. So the hardware is what we can build as an engineer or as a scientist. We have some components, but we want to figure this out. So this co-design would be based on, for example, we would do this chemical engineering or material design so that it can be put as what we want, and there will be involved a lot of fabrication process. So both methods would work to develop this as a closed loop to engineer convolve each other. So again, for this part, we want to achieve better functionality, like generate light or do this color as a decoration. But we can also achieve the best energy performance by using for example, the photonic material or the emissivity designs. And again, this frequency domain, you want to have the emissivity that can have a particular feature on certain frequency range, but rather in the, like for example, in our natural cases, most of the emissivity would be very engineered, and our design would significantly improve this performance. So let's summarize. So as we mentioned, we want to have the code design for both the photonic device as well as the functionality to control this. And we have demonstrated the 4 cases, but actually you can also check my other papers. It can share the same opinion. So the deep co-learning, so sometimes people think it's a very jargon word, but you need to know both the theory, control, and physics, and to do the real architecture to build this system together. And this process, in a traditional way, we will need to do this incremental reconfigurations and to gradually get this, for example, what kind of property we want to have in order to model the system. But now we put the, for example, you can have the better optimization, you can have the better in situ training as the algorithm, or you can also have, for example, develop the synthetic frequency dimension as a theory framework to further push forward this domain. And I think the chemical, for example, you use the material engineering to get the better performance. That's also a doable way. So we are the scientists and we are also the engineer to get the better functionality of the system. And we call this as an energy efficient system, but it's not limited by this. And we think we can do even apply this principle to even broader areas. Yeah. And thanks for my advisors. And this is the summary. And also, for example, we can also do some frequency count based on this principle, but based on the time, I will stop here and thank you for your time and attention.
For very nice talk. All of these opportunities about frequency engineering in photonics and the co-design, very, very exciting. Okay, any questions? The audience already asked a few questions. Yes.
Yes.
Thank you for the talk. It's very impressive. I liked it. We'll have a meeting later to say, but just one quick question. I'm interested about detection of open detection.
Yeah.
It seems like you have a 3D kernel, including time, right?
Yes. It's not. Yes. First of all, yes, but the time is actually the axis. It's not the real time. Like, yeah, we just use the z-axis to represent the time, but it's not a real time.
Yeah. So my question was like, if we have to flatten them to 1D, how do we do it in real time? But if it's already a data you already taken, then you don't need to take it in real time. I guess that's
in a time domain. Okay, I see. So in this case, for example, the video, we already have the time domain data, right? So we have everything together. But suppose you put this 3D data and then we don't do the real time configuration, but rather we want to process this chunk of data just to put, because for example, when you store the video on your computer, it's actually a 3D data. So that's the standard understanding. But the T, if you do the real time, that would be the, like, for example, the packet. I use the language as a packet, and then different packets, it would be the real time configuration. That's a so the answer is that we don't we do everything at the same time. Yeah.
It's a saved video.
Yeah. Or you can do the, for example, 3D data also includes point cloud. Oh, that's point cloud also. You can store this at the same time. Yeah. Thank you.
Questions? Not. Let's thank Lingling again. Nice work.
Thank you.